Hello friends, this is lecture number 5 of integral transform. Here we're going to discuss about the properties of Fourier transformation and their proofs as well, and also we're going to solve problem. And if you want to follow me on Insta, this is my Insta ID ozaloikazit123. And before we start, please subscribe the channel, also share with your friends, hit the thumbs up button and help me to grow my channel, inspire me to create new contents for you, right? And I have provided the links of previous lectures in the description box from lecture number 1 to 4. Then if you haven't watched those yet, then go through them, because for better understanding you should watch all the videos. Okay, so now let's start. So property number 1, this is the first property. If capital F1s and capital F2s, these are the Fourier transforms of two functions. Suppose small f1 as x and small f2 x. Here capital F1s and capital F2s. These two are the Fourier transforms of these two functions, right, respectively. Then the Fourier transform of a into small f1 x, b into small f2 of x is given by a into capital F1 of s, which is the Fourier transformation of small f1 x, plus b into f2 of s, which is the Fourier transformation of small f2 of x, right? So hope you have understood this. And here these a and b are constants, where a and b are constants. These are constants. Okay, so how to prove this? So let us prove this. So now you see, by definition, let me write it properly. Fourier transformation of this, copy this one. Fourier transformation of a into f1 small f1 as x plus b into small f2 of x is given by, according to the definition, minus infinity to plus infinity e to the power minus I s x. Then the function here a into f1 of x plus b into f2 of x dx. This is by definition, right? So what we can do here, Fourier transformation of this, just wait, let me copy this one. Is equal to, we can write here, since a is constant, so it can be taken out, right? A integration from minus infinity to plus infinity e to the power minus I s x f1 of x dx, and we can write b into, since b is constant, so it can be taken out, integration minus infinity to plus infinity f2 of x, sorry, I missed one thing, that is e to the power minus I s x f2 of x dx. That's what we got, right? Now you see, by definition of Fourier transformation, this is nothing but Fourier transformation of f1 of x, right? Similarly, this part is the definition of Fourier transformation of f2 of x, right? So what we can write here now, just let me clean these things, just wait. So we can write a into Fourier transformation of small f1 of x and plus b into Fourier transformation of small f2 of x, right? And we have already said that f1 is the Fourier transformation of small f1 of x, and f2, capital F2 of s, is the Fourier transformation of small f2 of x. So what we can write, a capital F1 of s plus b into capital F2 of S. That is what we needed to prove. So the linear property is proved, right? This is called linear property. This is called linear property. Now property number two. If the Fourier transformation, that is capital F of small f of x, this is the Fourier transformation of suppose here you see capital F of S is suppose the Fourier transformation of small f of x, then Fourier transformation of a into x, where a is a constant, will be given by 1 by a capital F of S by a, right? If you see this is the Fourier transformation of this, then Fourier transformation of f of a into small f of x, that can be given by 1 by a, and here this s should be replaced by s by a, right? That is the only difference. So hope you have understood this. And here a is constant. This is called change of scale property. This is called change of scale property, right? So now let's prove this property. Okay, let's prove it. So now here you see Fourier transformation capital F of here you see Fourier transformation of small f of x. Here it is given by capital F of S, and by definition this is equal to minus infinity to plus infinity e to the power minus isx small f of x dx. This is the definition of Fourier transformation, right? In different books, different authors use different definitions. Okay, so it may be different in different books. Okay, so all are correct. Here you see now Fourier transformation of small f of ax, by definition that's going to be given by minus infinity to plus infinity e to the power minus isx. Here this f of x is now small f of ax, right, dx. So if that is the case, then what we can do here, let us put ax is equal to t, and differentiating both sides with respect to x, we're gonna get a is equal to dt by dx, which is gonna give you dx is equal to dt by a. That's what we're gonna have. And also from here we're gonna have x is equal to t by a, right? So if we use this kind these results here, then what we're gonna have, capital F of small here Fourier transformation of small f of ax, that's gonna be equal to minus infinity to plus infinity e raised to the power is. Instead of x we're gonna write t by a. Instead of x I have written this. So hope you have understood, and it can be modified in this way, s by a into t, right? Then f of t dt by a, as it is constant, so a can be written outside the integral. So let me write one more step here. What we can do here, just wait. So we can write here that 1 by a integration from minus infinity to plus infinity e to the power minus I s by a into t f of t dt. Now if you compare the definition, these two are similar, right? Here, as we have instead of s we have s by a, so instead of s here we're gonna get s by a, right? And if you replace this variable by x, then you're gonna get this definition, and here instead of s, as we have s by a, so that's why the result is going to be this capital F of s, right? So what we can write here, let me cut it. Okay, so that's going to be equal to 1 by a capital F of s by a. When we had s only, then we had capital F of s, but here now we have s by small s, so we're gonna have capital F by s by, sorry, capital F of s by a. So that is what we have got. This is the Fourier transformation of small f of a x, right? And this is the property that we are to prove. So this is what we have proved. So hope you have understood this. So let's property number 3. So if the Fourier transformation of small f of x is capital F of s, then Fourier transformation of here, let me write Fourier transformation of the function small f of x minus a is given by e to the power minus I a s capital F of s, right? Capital F of s. Here a is constant. Okay, a is constant. Now let us prove this, and this property is known as shifting properties. So let me write it properly. This is called shifting property. Let's prove this property. Now you see, by definition, Fourier transformation of small f of x, which is capital F of s, that is equal to, by definition, from integration from minus infinity to plus infinity, e to the power minus I s x f of x dx, right? So therefore Fourier transformation of small f of x minus a, that's going to be given by integration from minus infinity to plus infinity, e to the power minus I s x f of x. Here instead of f of x, we're going to have x minus a dx, right? That's what we're going to have, right? So now let us put, sorry, or you can write putting x minus a is equal to 2, which is going to give you x is equal to, sorry, x minus a, I have used here t, which is going to give you t plus a or a plus t, same thing, right? T plus a or a plus t, right? And if you differentiate with respect to x both sides, you're going to get 1 is equal to dt by dx, which is going to imply that dx is equal to dt, right? So hope you have understood. If you use these results, then this is going to be equal to Fourier transformation of small f of x minus a, that's going to be equal to minus integration from integration from minus infinity to plus infinity, e to the power minus I s, x will be replaced by a plus t, x will be replaced by a plus t, right? A plus t, then f of x minus a is replaced by t, then dx is replaced by dt, right? So we're gonna get this. So from here, what we're gonna have, minus infinity plus infinity, so it can be written as e to the power minus I s a into e to the power minus I s t, right? So this part is constant, so that can be taken out of the integral, right? So if we do so, then what we're gonna get, so let me show you, then we're gonna have, just wait, e to the power minus I s a, integration from minus infinity to plus infinity e to the power minus I s t f of t dt, right? So simply replace the, if you assume that if you replace the t by x, that's going to be this one, right? And which is nothing but f of s, right? So by definition, what we're going to get, we're going to get f of s, right? So what we have done, replacing x by, replacing t by x, then we're gonna get e to the power minus I s a, and this is nothing but Fourier transformation of small f of x, and which is nothing but f of capital F of s, right? E to the power minus I s a capital F of s. So this is the right hand side. So hope you have understood this, proved. So this property is also property number 4. So if the Fourier transformation of small f of x is capital F of s, then the Fourier transformation of e to the power minus ax, where a is a constant, of f of x, Fourier transformation of this e to the power minus iax into f of x, that's going to be given by capital F of s plus a, right? So that is the fourth property. So let us prove this one. So here a is constant, okay? So now let's prove this, how to prove this one. So now let's prove this property. So here the Fourier transformation of small f of x is here capital F of s, and by definition that should be equal to minus infinity to plus infinity e to the power minus I s x f of x, right? This is the definition, f of x dx, right? So now by definition Fourier transformation of e to the power minus I ax small f of x, that's going to be equal to integration from minus infinity to plus infinity, and e to the power minus I s x by definition, then the function, this is the function here, this whole part. So we're going to write here e to the power minus I a x f of x dx. That's what we're going to have by definition, right? So now what we can do here, this can be written this way, minus infinity to plus infinity e to the power minus I s x minus I a x. So here we can take minus x common, minus I x is taken common, then what we're gonna get, it can be written as minus I s plus a into x, so f of x dx, right? So now here you see, if you observe, when there is only s, then it is capital F of s. Now we have s plus a, so that's why it's gonna be equal to capital F of s plus a, right? So hope you have understood this. So just let me write it properly, just wait. So this is that must be equal to capital F of s plus a by definition. So this is the right hand side, hence proved. So let me write the next property. So property number 5, if Fourier transformation of f of x is equal to capital F of s, then the Fourier transformation of small f of x into cos ax, that's given by half capital F of s plus a plus capital F of s minus a. So this is the property, and this is known as modulation theorem, right? This is known as modulation theorem, and let us prove this. So how to prove this one? So here you see, so Fourier transformation of function f of x, this is suppose capital F of s, that is defined as integration from minus infinity to plus infinity e to the power minus I s x f of x dx, right? This is the definition. So now let's find the find the Fourier transformation of this function, which is written Karl Beckett, you can see. So if we find that according to this definition, the Fourier transformation of small f of x cos ax, that's gonna be equal to integration from minus infinity to plus infinity e to the power minus s minus isx, and instead of f of x we have f of x into cos ax dx. That's what we have. So here we're gonna use this, let me use it. We're gonna use this, as we know that cos theta is equal to e to the power I theta plus e to the power minus I theta divided by 2. Let's use that. If we use that here we're going to consider ax as theta. Then what we're going to have, so we're going to have integration minus infinity to plus infinity e to the power minus isx f of x, and this is going to be e to the power iax plus e to the power minus iax by 2 dx. So this is constant, so it can be taken outside the integral, right? So we can write this way, that just wait. So we can write here 1 by 2 dx. We can write this way, right? So now, so it can be rearranged as this half Karl Beckett integration minus infinity to plus infinity, then e to the power this one into e to the power this, just wait, let me, e to the power minus isx into e to the power iax, that's going to be e to the power minus I. If we take minus ix common, then it's going to be s minus ax, right? We're going to get that, this product of these two, right? So if we have f of x here, then we can write f of x. So then what we're going to have, integration from e to the power minus I within bracket s minus a x f of x, then plus integration from minus infinity to plus infinity, then e to the power, if you multiply this one with this, so then e to the power minus isx minus iax. So from here minus iax can be taken common. So then what we're gonna have, then we're gonna have minus I s plus a into x f of x. That's what we're gonna have if you multiply this one with this, right? So hope you have understood this. So we can write, just wait, let me clean it. Okay, so what we can write here, give me a second. So we can write e to the power minus I s plus a x f of x, and oh sorry, I forgot to write the dx here. Just a second, just wait, f of x dx plus this one, then here also we have to write dx. Just let me have some space here. So f of x dx bracket closed. So that's how we can write. Okay, just do it, dx Karl Beckett close. So now you see, if you compare this one with this definition, here we have s, so here we can write capital F of s. So here we have s minus s, so we can write this as capital F of s minus a. Similarly, this one, it can be written as capital F of s plus a, right? So what's gonna be the result then? So then we can write, just wait, let me clean this. Okay, so therefore we can write that f of Fourier transformation of small f of x cos ax, that's going to be equal to half into, this can be written as capital F of s plus a. So I have written this one first, then plus f of this one is equal to s minus a by the definition of Fourier transformation. So this is similar to this one. Instead of s we have s minus a, so this s should be replaced by s minus a. That's it. Okay, so hope you have understood this. So this is proved. So next property is, Fourier transformation of first order derivative of f of x is given by is, capital F of s, if f of x, small f of x tends to 0 as x tends to plus minus infinity, right? So where this capital F of s is the Fourier transformation of small f of x, right? So now let us prove, and this property is called derivative theorem. This is known as derivative theorem. So let me write here, just wait, let me some space here. Okay, this is known as derivative theorem. Right, so this is derivative theorem. So now let's prove this one. So here you see, by definition, your Fourier transformation of small f of x, which is also written as capital F of s, is given by integration from minus infinity to plus infinity e to the power minus isx f of x dx. So Fourier transformation of first order derivative of f of x, that's going to be given by integration from minus infinity to plus infinity e to the power minus isx f dash x dx, right? By definition we're going to get this one, right? So here you see, if you use this product rule, that is integration of u v, that's going to be u integration of v minus integration u dash, then integration of v. That's what we're going to apply here. So if we apply that, so here we're going to take as u, this one as v. So in that case, what we're going to have, e to the power minus sx integration f dash x. So we know f dash x is nothing but derivative of f of x. So that's why if you integrate this, then you're gonna get f of x, right? So that's why we're gonna write, just let me keep this in the first step, f dash x dx, right? Let me write this way, then minus integration derivative of e to the power minus isx. If you differentiate it, then what you're gonna have, you're gonna have minus is e to the power minus isx. Then again integration of f dash x dx, then whole dx. That's what we're gonna have, right? So we are integrating it from, just wait, let me write it properly. This is dx. We are integrating it from minus infinity to plus infinity, right? So now you see, so if we integrate, then what we're gonna have here, e to the power minus isx. So integration of f dash x, that's gonna be f of x, right? F of x, integration from minus infinity to plus infinity, then here minus, that's gonna be plus, then integration, this minus is taken out, is, that integration from minus infinity to plus infinity, e to the power minus isx f dash x dx. That's what we're gonna have, right? So that's what we're gonna have. So here you see, as I have already mentioned here, if f tends to 0, as x tends to plus minus infinity. So for plus minus infinity, this tends to 0, so this part gonna be 0. So here what are you gonna have? 0 plus is, and this parts by the definition of Fourier transformation is nothing but Fourier transformation of f of x, right? Here we're gonna write, since f of x tends to 0 as x tends to plus minus infinity, right? So is, and this is nothing but Fourier transformation of small f of x is nothing but capital F of s, that we have already mentioned here, right? So hence it is proved. This is the proof of derivative theorem. This is nothing but Fourier transformation of first order derivative of the function small f of x, right? So hope you have understood this. Fourier transformation of a function of more than one variable. Now we have got that if f of x, which is a function of one variable, we know that its Fourier transformation f of x is equal to integration from minus infinity to plus infinity e to the power minus I s x minus I s x f of x dx. So this is the Fourier transformation for a function of one variable. Suppose we have a function of three variables x, y, z, then how to find its Fourier transformation? So it is a function of three variables. Function of three variables. So in that case, integration minus infinity to plus infinity, again integration minus infinity to plus infinity, integration from minus infinity to plus infinity, e to the power minus I s1 x, so you can take the minus I common, s1 x plus s2, we're gonna take s1, s2, s3 for three different variables x, y, z. So then y plus s3 z f of x, y, z dx, dx, dy, dz. That's how we're gonna find. So let's solve a problem using this concept. Okay, so question is, find the Fourier transformation, Fourier transform of e to the power minus r square by a is r square by a, where, so let me write it in red, where a is constant and r is equal to root over x square plus y square plus z square, which is a function of x, y, z, right? So let's solve this one. First, let me copy this question and let me go to a new slide. Okay, so here is a new slide we have. So we're gonna solve this question here. So now you see solution. So here f of r, that means which is a function of you can simply write f of x, y, z, which is e to the power minus r square by a square, where, sorry, not a square, only a, we have a, where a is constant, r is equal to x square plus y square plus z squares. So what gonna be the r square? It's gonna be equal to e to the power minus x square plus y square plus z square divided by a. So this is r square, right? So hope you have understood this. Now let's find the Fourier transformation of this. So Fourier transformation of f of x, y, z, that's going to be Fourier transformation of nothing but e to the power minus x square plus y square plus z square whole divided by a right? That's going to be given by integration from minus infinity to plus infinity e to the power minus I s1x plus s2y plus s3z into e to the power minus x square plus y square plus z square y square plus z square divided by a, and we can write just waiting dx dy dz. So this is what we're gonna have. Now it can be written as e to the power minus is1x into e to the power minus is2y, then into e to the power minus is3z, right? Similarly we can write this one as e to the power minus x square by a into e to the power minus y square by a into e to the power minus z square by a. Okay, and using that concept here we can write this way: integration from minus infinity to plus infinity e to the power minus is1x e to the power minus x square by a, then dx, then again integration from minus infinity to plus infinity e to the power minus s2y, then e to the power minus y square by a dy, then integration from minus infinity to plus infinity e to the power minus is3z e to the power minus z square by a dz. That's what we're gonna have. So this is what we have, that is the Fourier transformation of e to the power r square by a, right? So now let me copy this step and let me go to the next slide. Okay, so now let me go to the next slide. So here is the last step we have got. So in the last lecture I have already shown, I think just let me do it again. So here you see, first let me obtain the integration of this part separately. So integration of minus infinity to plus infinity e to the power minus is1x e to the power minus x square by a dx. How to integrate this? Now it can be written this way. So here you see, we can write this way. Then this part 1 by s1 x minus x square by a. So let me take the minus sign common, then it's gonna be x square by a plus 1 s1 x. It can be written in this way: minus x by root a whole square, then plus twice a. Instead of a we're gonna write 1 by root over x by root over a, this is twice a, into b. We should write I sine 1 root a divided by 2. If you cancel this 2, then you're gonna get this term, right? So hope you have understood this. Then this is a square plus twice a b, then we should have b square. So here the b is this one, so we're gonna get I s1 root over a by 2 whole square. As this term is not present here, so that's why again it should be subtracted, right? It should be subtracted, then minus I s1 root over a divided by 2 whole square, right? That's what we're gonna have. So therefore this part now can be written as x by root a plus I s1 root a by 2 whole square, and we have a minus sign here, this minus sign. Then just wait. Okay, here we have minus, On squaring I, we're gonna get -1, so this sign gonna be positive. S1 on squaring root a, that's gonna be a, and on squaring 2, that's gonna be 4. So we're gonna use this value here, right? So therefore what we're gonna get, then therefore we're gonna have integration minus infinity to plus infinity e to the power minus x by root a plus I s1 root a divided by 2 whole square plus s1 square root a divided by, sorry, not a, root a, that should be a divided by 4 dx. That's what we're gonna get. So now let me copy this step and let me go to new slide. So here it should be minus. Okay, now let me copy this step and let me go to a new slide. So this is what we have got, right? So now you see what we can do here. Let us put that x square by root a plus I s1 root over a divided by 2, that it let it be suppose t, and if you differentiate both sides with respect to x, this is a function of x, so that's going to be derivative of x is 1, so we're going to have here 1 by root a, then this thing's going to be 0 if you differentiate with respect to x, and derivative of t with respect to x, that's going to give you dt by dx, right? And which implies that dx is equal to dt by into root a into dt. That's what we're gonna get. So using these results, what we can write, integration minus infinity to plus infinity e to the power minus I s1 x into e to the power minus x square by a dx, that's going to be equal to integration from minus infinity to plus infinity e to the power minus, we have considered this part as t, so that's going to be t square. Then here you see this can be written this way, into e to the power this, we can write this way. Hope you have understood this. So now if that is the case, then here you see this is a constant part, so it can be taken outside the integral, so we can write this way. Just wait, just give me a second. So we can write here e to the power s1 square a by 2, that's what we can write. Let me write it properly. E to the power I s1 a, I is not there, s1 a divided by 4, that's what we have got, e to the power equal to this one, right? So again, instead of dx, we're going to put a dt, so root a is constant, so it is taken out, and here we're going to have dt. That's what we have got, right? So just wait, let me write it properly. And how to evaluate this now result of this integration? Here you see minus infinity to plus infinity minus t square e to the power minus t square dt, it can be written. So as there is t square, it must be an even function. If this is even function, then 2 it can be written to integration from 0 to infinity e to the power minus t square dt. And this is a very important result, so remember it. Or if you want to know how we have got, then you can watch the previous lecture. Link is provided in the description box. There I have explained why this value of this part is root pi by 2. Okay, I have already shown this. So you can use this result directly. Okay, this is equal to pi, you can use this one is equal to root over pi directly. And if you want the explanation, then visit the lecture number what's the lecture number 4, okay, last lecture. So here what we're gonna have, so as I have already told you, this is root a e to the power e to the power s1a by 4. This can be written as 2 into 0 to infinity e to the power minus t square dt, and which is equal to, so a root over e to the power s1a by 4. This part is equal to pi, we have already got here. So root pi, not only pi, root pi. That's why it can be written this way. This is also root, this is also root. So it can be written this way, that just wait, root a pi e to the power s1a divided by 4. We can write this way. So we have got this result. This is here you see, just wait. This is equal to what? Integration of minus infinity to plus infinity e to the power minus I s1x into e to the power minus x square by a dx. And this is what we have got, right? So similarly, just let me copy this one and let me go to the next slide. Okay, so here you see we have got this. Similarly, just wait, similarly we can find integration from minus infinity to plus infinity e to the power minus I s2y e to the power y square minus y square by a dy. That's going to be equal to, again, root a pi e to the power s2 a by 4. And similarly, we're going to get integration from minus infinity to plus infinity e to the power minus I s3 z e to the power minus z square by a dz. That's going to be equal to you see root over a pi, again, e to the power s3 by s3 into a by 4, s3 into a by 4. That's what we're gonna have, right? Just wait, let me little bit of adjustment. So just wait. So here we can write and, okay, this is what we're gonna have. Let me write it clearly. E to the power s3 divided by 4. That's what we have got. So let us use these three results here. Let me go back to the previous slide. So here you see we can use this three result here. So let me copy this. This is the Fourier transformation of the required function. So this is the Fourier transformation of e to the power r square minus r square by a. So this can be replaced by this value, this can be replaced by this value, and this can be replaced by this value. And doing so, what we're gonna have, so let me write, this is equation number 1, right? This is equation number 1. Just let me go back. This is suppose equation number 1. Okay, so using these values, so using these results in equation number 1, we have, so let me replace this one by its value. What is it? Its value, this one, root over a pi e to the power s1a by 4. So similarly, let us replace this one by this value. Then what we're gonna have, root over a pi e to the power s2 a by 4. Then let us replace this one by this value. Then what we're gonna have, we're gonna have root over a pi e to the power s3 a by 4. That's what we're gonna have. So now here you see, if you multiply this 3, then what you're gonna have, a pi whole to the power 3 by 2, right? 3 by 2, because we're gonna have a this is root over, means it's power 1 by 2, right? If you multiply 3 root over a pi 3, so we have root over a pi, root over a pi, root over a pi. So if you multiply this 3, then there should be a cube, so who is implies who is going to give you this
right? A pi by 3 by 2, a pi root over 3, a pi whole to the power 3 by 2. That's what we're gonna have. Then if you multiply this 3, then we're gonna have e to the power, a by 4 can be taken common, s1 plus s2 plus s3, a by 4. That's what we're gonna have. So this is the answer, right? So hope you have understood this. This question was asked in BSc 4th sem, BSc 4th sem in 2023 of Dibrugarh University, right? So hope you have understood this, and if you have understood, please do like my videos and share with your friends. Help me to grow my channel, inspire me to create new contents for you. So do subscribe to the channel. Thank you for watching. See you in the next video.